Hello, in this video we're going to focus on a dam that is approximated as a trapezoid with a total vertical height h and a top and a bottom width t and b. And with this dam, the water level is at a level lowercase h, and we're trying to find an expression for the horizontal force exerted by the water on the dam. And so to get a better picture of this problem, we can start off by drawing the situation. So here is our dam that is approximated as a trapezoid. We can exaggerate the trapezoid a little bit more. So here's our dam, and we said the total height is capital H, the water level is at lowercase h, and the top and bottom widths are t and b. And so we're trying to find an expression of this water here. We're trying to find the expression of the force exerted by this water, the horizontal force exerted by this water on this dam in this direction. And so one more thing I would like to consider is drawing a side view of this dam so that we can consider the possible effect of the atmosphere on the pressure and the force on the dam. And so here's a side view of this dam. And here is the water. Here's the water level, h, and here's the entire height h. So we're trying to find an expression for the horizontal force of the water in this direction on the vertical dam that is in the shape of a trapezoid. However, what about the atmosphere here that has a pressure, an atmospheric pressure? And what about the atmospheric pressure here? Well, it will provide a force in this direction on the dam, and the atmospheric pressure here will provide a force in this direction. And so this atmospheric pressure, since we know that force is pressure times area, since we know that the force due to the atmospheric pressure at the top will be the atmospheric pressure times the total area of the dam. And so what about right here on the right? It will be the opposite direction. We'll have to subtract the force, which is the atmospheric pressure times the area, the total area of the dam. And so they will cancel out. By observing that the two atmospheric pressures that act on the dam, their forces cancel out, so then we can conclude that we can work with gauge pressure and not worry about the atmospheric pressure. So gauge pressure, since we know that they cancel out. Now back to the front view right here. So a few things we need to keep in mind before trying to find an expression for the horizontal force of the water on the dam is the very basic equation that pressure is force over area. And the force, the only force that we have, will be due to the gravitational force, and so that'll be m, the mass of the water, times g over the area. And we know that since we know that the density is the mass over the volume, we can manipulate this to say that the mass is also the density times the volume. And by replacing this, we arrive at the density times the volume times the gravitational acceleration over the area is the pressure, but we can simplify this even more. We know that the volume is the area times the height. The height, or we can call it in this case y, since we already called this little h. So from here, we see that the pressure is equal to density area times the height times g over the area. And the areas cancel out, and we get that the pressure is rho g y. From this, we note that since the pressure is rho g y, and we assume that the density and the gravitational acceleration are both constant, we can observe that the pressure is dependent on the depth. Since the pressure depends on depth, y, we have a variable pressure. So that is one thing that we need to keep in mind when trying to find an expression for the force of the water on the dam, that the pressure going down from lowercase h to the bottom of the dam will have a variable pressure. One more thing that we need to keep in mind is that when looking at this dam, we know that it has a trapezoidal shape. It's not a very good trapezoid, but the point is, since the dam is in the shape of a trapezoid, its area, well, we know that the width of the dam is not constant. Here it's this long, here it's shorter. And so besides having the pressure being variable, we also have the area being variable, since we know the area is dependent on the width and the height. So keeping these two things in mind, we realize that finding this pressure, this horizontal force of the water on the dam depends on the pressure in the area, which both are variable. And so we can start off by something simple. We know that the force, pressure times the area. And we know since the area is variable, the force will be variable. But one thing we can keep in mind is that if we redraw this trapezoidal dam, we can take infinitesimally small bands that each have their own infinitesimal area, and consequently they have their own widths as well as their own heights. You can call it dy. A band here will be different than a band here. They will all each have their own pressure, dF, since they have their different depths, which changes the pressure, and they have varying widths, which change the area, and the force is dependent on both the pressure and the area. So what we can do now is, since we know that each band of infinitesimal area will have its own force, the pressure in this band we can assume will be constant. Since it's so small, the pressure will not change from here to here, which is dA. So we can keep that constant, and we have dA from here to here. And so from this, we know that we can replace this pressure with what it's more dependent on, something that tells us more. It's dependent on rho g y, where these are constant, but it does truly depend on the depth. It changes. That's why the pressure is variable because of the depth, the varying depth in the water. Okay, so we can write dF equals rho gy dA. What about dA? When we're trying to find an expression for dA into this equation, what does that even mean? It means we're trying to ask, how is the area changing? How is the area of this trapezoid changing as you go from the top to the bottom? Well, we know that here is the trapezoid. We can draw one more time. We know that here at the top, what is the width? T. That's what the width is. What about the top? We called it B. Okay. Now, what about the height? Well, we can call here the depth, y, equals 0. We start off at 0, and we go all the way to h. Well, now we have 2 points. We have t, t0, and bh. Well, we can easily note that this width that's changing with the depth, how does it change with the depth? Well, it's linearly dependent on the depth. And we can get the slope of this. The slope would be just the slope formula. So we could say b minus t, the width here, and the width here, minus the width here, over h minus 0. And so we get the slope being b minus t over h. That is the slope of the equation of the line, which represents how the width changes as you go from the top to the bottom of this trapezoid. Well, since that's the slope, what is it dependent on? It's dependent on the depth, y. Okay, so m is b minus t over h. Well, the line will be starting from the top, t, right here. That is the intercept, since we're starting there. And then to that intercept, we will add how the line is changing. B minus t over h, the slope, times the dependent variable, y. This is how the width changes with the depth, w of y. So now, since we have an exact equation that represents the changing width, now we can write something for dA, the area that changes from here to here and so on. Well, we can write our original equation, dF rho gy dA will be replaced. Well, what is dA? If we originally had a vertical dam, but instead of a trapezoidal shape, we just had a rectangular shape, well, the force is going to be acting this way, but the area is simply the width times the height. Well, the pressure is still dependent on that changing y, but the width is constant throughout. The width here is the same as the width here, and so dA would be the width times dy. But in this case, our width is changing by the equation we derived right here. And so dF is equal to rho gy times t plus b minus t over h y times dy. And now from here, what does this equation right here tell us? This tells us that the force exerted by the liquid on a small portion dA within this trapezoidal dam will be dependent on the depth, and assuming that these are constant, the density and the gravitational acceleration, all this is dependent on is the depth. And now we can take the integral of both sides in order to sum up the total force along from the bottom of the dam to the surface of the water. And we can do that by taking the integral of both sides, like this. The integral of df is equal to f. And now, we know, I think it's simple to just distribute this into both of these, so we can get the integral of rho gy t plus rho gy b minus t over h times y, all of that dy. Well, something very important is to keep in mind the limits of integration. Well, we know that we're trying to sum up here the force df along this entire trapezoid. Well, we know we're going up until little h, the surface of the water. From the bottom of the dam to the surface of the water. This is where the fluid is. Well, we know that we called the top here y equals 0, and we called the bottom here y equals h. Well, then the surface of the water will be y equals little h. And then we will be going from little h to big H. And so we're going from depth y equals h to y equals big H. And we can easily integrate this, knowing that the only variable of integration is y, since we're integrating with respect to dy. We get rho gt over 2y squared plus rho g b minus t over h over 3y cubed, since we had a y squared here. And that is from y equals h, little h, surface of the water, to the bottom of the dam. And from this, we would simply integrate, we would plug in big H and little h, and we will get rho gt over 2 h squared plus rho g b minus t over 3h h cubed minus rho gt little h squared over 2 plus rho g b minus t little h cubed all over 3 big H. And you can do some simplifications, such as simplifying this cubed h with this h. And that is about it. But using this equation, what are the variables here? We have the density, gravitational acceleration, which we assume both of these are constant. We have T and B, which are the widths of the dam, the top and bottom widths. We have big H, which is the entire height of the dam. In this case, where I solved it, this corresponds to y equals h is the bottom of the dam. And lastly, we have little h, which is the surface of the water. Using this equation, this is the expression for the horizontal force exerted by the water on this trapezoidal dam, knowing the top and bottom widths of the dam as well as the total height and the surface of the water.